Alright, so here we begin discussing Strassen's theorem and the relationship between metrics in section 4.3. So right away let me mention that in this entire section we will always assume that the metric space we are dealing with is separable. And the reason for this is that we will work with pairs of random variables, let's say x and y, defined on the same probability space and taking values in our metric space S, and we'll be looking at the distance between these two random variables. And in order for the distance to be a measurable function, you need some assumption on the metric space. So for example, if you look at the set where x and y are equal to each other, okay, so the distance between them is 0. If you want this set to be measurable, you already need some assumption on the metric space. For example, if the metric space is not separable, you can construct an example where this diagonal will not be a measurable set. Okay, so for that reason, we will always assume that the metric space is separable. Of course, it will be used in other ways in the proof of Strassen's theorem itself, so it will also be an assumption there, but we need this assumption even earlier. In particular, we begin here by defining the so-called KeyFun metric on random variables. Okay, and the definition of this metric is that given these two random variables x and y on the same probability space, you define this quantity alpha xy, which is the infimum over all positive epsilon, okay, such that the probability that the distance d between these random variable x and y in the metric space bigger than epsilon, okay, this probability of this set is less than or equal than epsilon. Okay, so in other words, if this quantity alpha is less than epsilon, it means that these two random variables x and y are within distance epsilon from each other, except maybe on a set of measure epsilon. Okay, so that's the definition of this the so-called KeyFun metric. Okay, now it's easy to check that the infimum in this definition is achieved, and in fact this is just continuity of measure. If you let alpha go to this infimum, epsilon go to this infimum alpha, you will see that probability that the distance between x and y bigger than alpha also satisfies this inequality, and so the infimum here is achieved. So you can just write the same control of the probability with alpha. You know, in particular, if alpha is 0, this means that probability that the distance between x and y is strictly bigger than 0. In other words, x is not equal to y. This will be 0. Okay, and what this means, of course, that these two random variables x and y are equal to each other almost surely. Okay, so if you want to think of this quantity as a metric, in particular, you have to identify functions up to a set of measure 0. Okay, so the definition here depends on the probability measure on our metric space. But if you think of this equivalence, then this becomes indeed a metric, which is very easy to check. I'm not going to do this here. And in particular, it's also a simple calculation to check that you have this lemma that says that alpha metrizes convergence of random variables in probability. Okay, meaning that random variable, sequence of random variables xn converges to x in probability. It's if and only if they converge in this metric that we just defined. But for us, the main interest in this section for this quantity, for this KeyFun metric alpha, will be its relationship between with the Levy-Prokhorov metric. Okay, so we'll be really discussing Levy-Prokhorov metric and its relationship with the KeyFun metric. Okay, and we start here with the following simple observation, that given these two random variables x and y above, if you consider their distributions and look at the Levy-Prokhorov metric between the law of x and the law of y, which are probability measures on this metric space S, this will be bounded by the KeyFun metric alpha between random variables x and y. Okay, so it reflects, this kind of clear intuition that the closeness of random variables as functions, it's a stronger than the closeness of their distribution. But here the definitions of Levy-Prokhorov metric and KeyFun metric, in some sense, they match each other. You have this quantitative relationship between these two quantities. And of course, the proof of this is in this direction. The proof is pretty straightforward. Okay, what you do is you take any epsilon bigger than this KeyFun distance between random variables x and y, and in particular, by definition, it means that probability that the distance between these two random variables exceeds epsilon is bounded by epsilon. Okay, so here I'm taking alpha to be slightly bigger. I'm taking epsilon to be slightly bigger than this alpha to be able to write the non-strict inequality here inside the probability. And then, if you recall the Levy-Prokhorov distance, the definition of Levy-Prokhorov distance, you want to compare distribution of x with the distribution of y in the following way. So distribution of x is just a probability that x belongs to some measurable set in our Borel sigma algebra in this metric space. And to compare it with the same, with the similar quantity for the distribution of y, we have to sort of replace x by y. And the way we do it, we just split this event into two pieces. Okay, when the distance between x and y is less than epsilon, and when it's bigger than epsilon. Right now, on the first event, if x is in A and y is within distant epsilon from x, that means that y is in the epsilon neighborhood of this set A. And on the second event, we just drop the set x belongs to A and just leave the probability that the distance is greater or equal than epsilon, which is less than epsilon, less than or equal than epsilon by the choice that we made above. So this probability is less than or equal than epsilon. And we see that this is exactly the relationship that we want in the definition of Levy-Prokhorov metric, right? That the probability in terms of x can be bounded probability in terms of y for some epsilon neighborhood of this set A plus epsilon. Okay, so the conclusion here is that the Levy-Prokhorov distance between the law of x and the law of y is bounded by epsilon. And then we took epsilon to be strictly bigger than alpha, and then we take limit epsilon goes to alpha, and we get the inequality in this lemma. Okay. So in this direction, it's, as you can see, it's very easy to show, because the information that two functions or two random variables are close to each other except on a small set is very strong, and so we immediately get this information about the closeness of the distribution of x and y. Now, in the other direction, or let's say what's the main point of the Strassen's theorem that we are going to prove here, is that you can, in some sense, reverse this statement. namely, if you are given two probability measures, P and Q, and let me denote the set of all probability measures by, as we did by this notation here. And then you know that the Levy-Prokhorov distance between these two probability measures is less than some delta. Then what Strassen's theorem will achieve is construct two random variables, or let's say construct both a probability space omega with some probability measure mu. Now here I will distinguish the probability measure on this probability space that we'll be constructing, because P is already reserved for this probability measure on the metric space. So we'll construct some probability space with a measure mu, and we'll construct random variables x and y as above on this space, taking values in S, such that, okay, first of all, the distribution of x, the law of x will be P, the law of y will be Q, and that these two random variables will be close in the KeyFun metric. So the this probability measure mu on our probability space of the event that the distance between these two random variables exceeds delta will be less than or equal than delta. Okay, so in other words, the KeyFun metric will be less than or equal than delta. Okay, by the previous lemma, for all random variables x and y with distributions p and q, you can control Levy-Prokhorov distance by KeyFun metric. And the Strassen's theorem will tell us that for some choices of this x and y, so we can construct special choices where you basically get equality there. Okay, that if you take delta slightly bigger than the Levy-Prokhorov metric, then the same delta will also bound the KeyFun metric for this special choice of x and y. And in some cases, under the assumption that p and q are both tight probability measures, for example, if our metric space is complete, in addition to being separable, you can actually get exact equality there. Okay. And the way this construction of the probability space and random variables will be done is very concrete in some sense. It will be as follows. Okay. I made a picture here that shows what the probability space will be. So of course we'll do the construction on the sample space for this pair of random variables x and y. So in fact, our probability space will be just the product space of the metric space S with itself. Okay, and the point in the space will be just a pair of coordinates x and y. So, you know, if you want to think of a point omega in this probability space omega, it will be just this pair of coordinates x and y. And the random variables that we'll construct will be actually just the coordinates x and y themselves. So the random variable x here will be as a function of this omega, or the pair xy, it will be just the coordinate x. Okay, and the random variable y will be the coordinate y. Okay, so the random variable y here will be just the second coordinate. And then our goal will be really to construct this probability measure mu, and since the random variables already fix and we want their distributions to be p and q, okay, we'll use this notation that the probability measure mu on this product space, which has marginals p and q, will denote such sets, or the collection of such probabilities, by m p and q. Okay, it will be the same notation that we'll use in the next section, but it's also convenient here. So what this notation means, that the probability measure mu on this product space is such that the distribution of the first coordinate, which we already denoted as a random variable by capital X, is just this probability measure p, and the distribution of the second coordinate y is this probability measure Q. Okay, that will be this notation for probability measures with the given marginals P and Q. And we'll construct the probability measure starting from the marginals P and Q such that it mostly concentrates near this diagonal with the size delta. Okay, so in other words, what we want is that the measure of all the points x and y at the distance greater than delta should be less than or equal than delta. Okay, so the set inside this probability measure here is exactly this set outside of the diagonal, and we want the set outside of this neighborhood of the diagonal to be of size delta, right? So in particular, this means that the KeyFun metric between this diagonal, or between the coordinates x and y, will be bounded by delta. And so since we chose delta to be anything slightly bigger than the Levy-Prokhorov metric, that's exactly what we want. So we'll be working with basically the sample space where the random variables will be just the coordinates, and we'll be constructing this probability measure given its marginals excuse me, that basically concentrates as much as possible near the diagonal. If we know that and the size of the diagonal corresponds to the Levy-Prokhorov distance between these probability measures, these marginals P and Q. Now, interestingly, the theorem itself will be stated in a little bit more flexible way. So if you look at the notes, the theorem itself is stated with some extra parameters to give ourselves a flexibility in the proof. So let me state how the theorem appears in the notes. Okay, so the Strassen's theorem is, well, first of all, let me remind you that we have this assumption that the space is separable, and then we are given these two probability measures P and Q on this space, and we'll also be given two parameters, A and B, bigger than 0. So these two parameters will be just like a parameter epsilon in the definition of the Levy-Prokhorov metric, except our assumption here will be a little bit more flexible. So instead of the assumption on the Levy-Prokhorov metric, we'll make the following relaxed assumption about the relationship between these two probabilities P and Q. Okay, we'll say that the probability given a set F with respect to this measure P can be controlled by Q of A neighborhood of F plus B, okay, for all Borel sets on our probability space. So in the Levy-Prokhorov metric, we would choose this A and B to be the same. Here it will be convenient to choose them different to allow us some flexibility in the proof. Okay, and then given this assumption, then for any epsilon greater than 0, we can find a probability measure mu. And again, here this probability measure will be broken into two pieces, which is just for the reference to the proof itself. So the way the proof will go, we'll construct two pieces in this measure, eta and gamma, where well, the measure will be on the product space, and it will satisfy the following conditions. That, of course, the first condition will be that the measure mu, just like we want, it has marginals P and Q, so the coordinates will have distributions P and Q. And then this piece eta will be a good piece concentrating near the diagonal, that the measure eta outside of the diagonal, so when the distance between the coordinates is bigger than a plus epsilon, this will be 0. Okay, so the diagonal here will be of size a plus epsilon. And we are giving ourselves a little bit of this epsilon of room in addition to the parameters a and b in this assumption, Levy-Prokhorov type assumptions. Okay. And then the piece gamma will be just a small additional piece where, you know, the exceptional event happens, right? Where we don't control the distance between our coordinates, but the size of this piece will be small and will be controlled by the second parameter b plus this epsilon room. Now, moreover, the way the proof will go, it will give us additional structural information about this measure mu. It turns out that it can be constructed as a finite sum of product measures, okay, which can be convenient in applications. Now, in particular, if we want to use this, you know, more flexible statement in this theorem to get the result as above, we simply have to take these parameters a and b to be the same, and basically we can take them slightly bigger than this Levy-Prokhorov metric. So you take them to be equal to Levy-Prokhorov metric plus arbitrary epsilon. And then in the statements 2 and 3 here, we have a plus epsilon and b plus epsilon, okay, which in this case will be Levy-Prokhorov metric plus 2 epsilon. This will correspond exactly to the delta that we had in the statement above. But for the convenience of the proof, okay, we give ourselves this flexibility with these parameters, and also we'll be kind of constructing the good piece and the bad piece sometimes separately. So for that reason, we present the statement of the theorem in such a way. Now, the assumption in the above theorem can be replaced by a similar assumption, let's call it assumption star, which looks identical, but instead of all Borel sets, you can require this, for example, for all closed sets. Okay, sometimes you can maybe check this just for all closed sets, or you could also do it for all open sets. And the point here is that this assumption with, let's say, all closed sets will imply the above assumption, which appears stronger, right? For all, here you had all Borel sets, with the only difference that A will be replaced by, let's say, a plus epsilon, or maybe a plus 2 epsilon, right? And b will stay the same. And that's because we give ourselves this epsilon of room, so it doesn't really matter that if we, you know, change epsilon into epsilon plus we change a into a plus 2 epsilon. We can use the stronger assumption, if we like, starting from this weaker assumption. Right, and the reason is because if you start with arbitrary set, what you can do first is you can take its epsilon neighborhood and take the closed. For example, if you start with closed sets here, you can take a closed epsilon neighborhood. So in other words, you can consider a set of all points S within distance less than or equal than epsilon. Right, so this will be a closed set. And then if your assumption star here holds, then you can bound this by the A neighborhood plus B. Okay, and of course you can then say that if you took epsilon neighborhood and then closed it and then took another A neighborhood, this will be inside A plus 2 epsilon neighborhood. And you get the stronger assumption now for all Borel sets, just with A replaced by A plus 2 epsilon. So that's why sometimes you see the statement of this theorem just for all closed sets, but right away we can start with a stronger assumption for all Borel sets. We'll discuss the proof of this theorem in the next video, but let me now discuss some of its consequences. All right, so first of all, we just said that if you take this A and B to be the same and slightly bigger than the Levy-Prokhorov metric, then you can find this, you can construct this probability measure on the product of metric space with itself with these marginals, right, that satisfy the inequality that we wrote above. So in particular, let's take this quantity A and B slightly bigger than rho to be of the form rho plus 1 over n, where rho is the Levy-Prokhorov distance between P and Q. In other words, this was like the epsilon in the statement, right? So given this epsilon, we can find the measure mu, which I will denote here mu n. And all these mu n's, they have marginals P and Q, in addition to satisfying this inequality in the definition of the KeyFun metric. Now the question here is, can we let n go to infinity and get a cleaner statement without this epsilon, just, you know, exactly showing that the metric mu can be chosen with KeyFun metric between the coordinates x and y exactly equal to rho, okay? And under some assumption, of course, it turns out that yes, we can do that. So that will be this first observation here, that if the measures P and Q are tight, in particular when your space S is complete, right, by Ulam's theorem, then indeed you can find this measure mu with marginals P and Q such that the same inequality is satisfied without epsilon, or with epsilon equal to 0. Okay, so it's the cleaner statement of the Strassen's theorem under this additional assumption when P and Q are tight. And the proof here, of course, just passing to the limit in the statement above, and using the fact that, you know, since P and Q are tight, we have a compact K such that these probability measures concentrated on this compact, then the complement has weight most epsilon for both of them, right? Of course, this implies that because mu n has marginals P and Q, right, then it satisfies the inequality that the measure mu n outside of the product of this compact is less than 2 epsilon. Of course, that's because you know, the complement of k times k, it means either the first coordinate is outside of this compact or the second coordinate is outside of this compact. And the coordinates have measures P and Q, so by the union bound you get at most 2 epsilon. But of course that means that this sequence of probability measures is uniformly tight. Which implies that there is a converging subsequence, so you can find a subsequence nk such that this will converge to some limit mu. And then you just have to check that this limit satisfies the inequality that you want, okay? And the way you do it, if you consider the set away from the diagonal by the distance rho plus some epsilon, Well, this is an open set, so here you can use portmanteau theorem. So by portmanteau theorem, this probability, which is the limiting probability, is less than the Lie-minf along this subsequence of the same statement for the measure mu n k. But for the measure mu n k, we already had the statement where we can control the probability outside of the diagonal, away from the diagonal by more than rho plus 1 over n. Okay, and we have this inequality because eventually nk will get smaller, 1 over nk will get smaller than epsilon. But this probability, or the measure of the set, was bounded by rho plus 1 over nk, and so this limit will be bounded by rho. So 1 over nk disappears and you just get this upper bound rho. Okay, and then you just let epsilon now go to 0 and use continuity of measure to conclude that the measure mu of this set here will be also bounded by rho, right? And that's exactly what we want. We get the statement for this limiting measure mu as in the statement of Strassen's theorem, just with epsilon equal to 0. All right, and then finally I want to mention the main consequence that we want to discuss here as an application of Strassen's theorem, namely relationship between the Levy-Prokhorov and the bounded Lipschitz metric. Okay, so we have the following consequence, that again, if the space is separable, so I said everywhere here we assume that the space is separable, then the bounded Lipschitz metric between two probability measures on this space is less than or equal than twice the Levy-Prokhorov metric between P and Q. And this is in addition to inequality that we had before, that the Levy-Prokhorov is bounded by twice square root of the bounded Lipschitz metric. Okay, so now we have this two-sided relationship between these probability measures, and so they are indeed equivalent and with these precise inequalities. And given the Strassen's theorem, the proof of this new inequality is pretty straightforward. So you construct the random variables x and y as before, so we constructed them as coordinates on the probability space, but here it's just convenient, you know, to think of this more abstractly. So we constructed random variable x with the distribution p and y with the distribution q, such that the KeyFun metric between x and y was less than Levy-Prokhorov metric between their distributions p and q, maybe plus little epsilon, okay, if we don't have any additional assumptions like tightness. Now, if we want to control the bounded Lipschitz metric, we have to take some bounded Lipschitz function on our metric space, right? And the way bounded Lipschitz is defined, you take a supremum over the unit ball in the bounded Lipschitz functions of integral of f with respect to p minus integral of f with respect to q. Okay. So you want to be able to control this difference here. Well, in terms of these random variables x and y that we constructed, since they have distribution p and q, this is just expectation of f of x and expectation of f of y. And then we'll just take the absolute value inside the integral. So okay, we can bound it by this quantity here. And then to use the information about the KeyFun metric, we will break this integral into two pieces. Okay, so one piece where the distance between x and y is bounded by rho plus epsilon, and the complement. And when you consider the integral, this expectation on the first set, okay, because f is a Lipschitz function and x and y are within distance rho plus epsilon of each other, right? The difference between f of x and f of y will be bounded by the Lipschitz constant of this function f times the distance times rho plus epsilon. Okay, and the integral on the second piece, when x and y are further apart, well, in that case we just bound both f of x and f of y by the sup norm of f, so the difference will be bounded by twice the sup norm of f, and you're left with the probability that of this set, that the distance is bigger than rho plus epsilon. And the way we chose, or the way we constructed x and y here, right, that's exactly when the KeyFun metric is bounded by rho plus epsilon, right? So by definition, this probability here is bounded by rho plus epsilon. So as a result, we get that the sum is bounded by twice Lipschitz norm plus L infinity norm times rho plus epsilon, which is twice bounded Lipschitz norm rho plus epsilon. Okay, and now when you take a supremum over bounded Lipschitz function with bounded Lipschitz norm less than or equal than 1, you get exactly the bounded Lipschitz distance between P and Q is less than twice the Levi-Prokhorov distance between P and Q plus epsilon. Okay, and then to conclude the proof, you just let epsilon go to 0. Okay, so that proves this new inequality in the relationship between beta and rho. Okay. All right, so this concludes just a general overview and discussion of the Strassen's theorem, and in the next video we will discuss the ideas in the proof of this theorem.